This is in continuation of the lecture series on phase equilibrium that I will be discussing today. Two more one component systems. Before I start today's lecture, let me just recapitulate what we studied in this topic so far. Phase rule equation we have derived. Before that, we have explained the terms involved in this topic, which recur quite often, and then application of phase rule to one component system, and we have applied it to water system. In today's lecture, I will continue with one component systems, and I will discuss two more phase diagrams, one of carbon dioxide and the other is of sulfur. There are many more phase diagrams, but then these three will illustrate how phase rule can be applied successfully in extracting information from these diagrams. Let me begin with carbon dioxide system. Like water system, carbon dioxide system is also a one component system which exists in one solid, one liquid and a gas phase. But there are differences, and in fact the phase diagram of carbon dioxide system is a representative of one component systems, and as we know, water always behaves differently. It is an exception. So, it is a one component system, C is equal to 1. We can go stepwise and try to apply phase rule equation to this. Putting P is equal to 1, that means the system is present only as one phase, solid, liquid or gas. We get the maximum number of degrees of freedom. F is equal to 1, the number of components, minus 1, number of phases, plus 2 gives a value of 2, the number of degrees of freedom, and which tells us that at least 2 variables are necessary to describe the condition of a phase. Pressure and temperature are the choice for us to construct a phase diagram. Let us directly go to carbon dioxide system and apply phase rule, and what we get: solid, liquid, gaseous states of or phases of carbon dioxide. F is equal to 2, and our experience tells us that there will be 3 areas of stability, one for each of these phases. Then there are 3 possibilities of having 2 phase equilibria, which are univariant systems, and each one will be represented by a line. So, there will be 3 lines. The 3 equilibria are carbon dioxide solid in equilibrium with carbon dioxide liquid, carbon dioxide liquid in equilibrium with carbon dioxide gas, and carbon dioxide solid in equilibrium with carbon dioxide gas. And there is a possibility of a 3 phase equilibrium. When that happens, number of degrees of freedom becomes 0, the system becomes invariant, and it is represented by a point. This is what we have seen in the case of water system also. I am repeating this so that you become familiar with the application of phase rule equation. Let me start with the diagram, how it looks like. This is exactly similar to water system, but some differences which will become obvious as we move forward. There are 3 regions of stability for solid carbon dioxide, liquid carbon dioxide and gaseous carbon dioxide. These are bivariant systems represented by areas, which means that we have 2 degrees of freedom. We can arbitrarily fix pressure as well as temperature. But then there are lines. Each line represents a 2 phase equilibrium. This is the equilibrium between solid carbon dioxide and carbon dioxide gas, and we can name it safely as the sublimation curve. The conversion of solid to vapor or gas directly is known as sublimation. Similarly, we can name the line OB. In this case, the equilibrium is between solid carbon dioxide and liquid carbon dioxide, and we can call this line the melting point curve or the fusion curve. This gives us the pressure and temperature conditions at which this equilibrium is established, and the last line that we have is OC, which gives us the pressure temperature combinations which give us the equilibrium between liquid carbon dioxide and gaseous carbon dioxide. As we know, the line terminates at point C, which is the critical point, and above which the liquid and the gas become so similar that they become indistinguishable. But here is the point O at which the three lines intersect. This is the triple point for carbon dioxide system. This is the invariant point. As we know, it is characteristic of the system simply because the system decides the pressure and the temperature corresponding to this point. We have no degree of freedom, and in the case of water, we have seen that these values of temperature and pressure corresponding to the critical point are used in developing scales, like absolute scale of temperature is based on the value of temperature corresponding to the triple point temperature of water system. Now, after looking at this diagram, we are tempted to compare it with the phase diagram of water system. The comparison is shown here. Two phase diagrams are put on the same drawing. Both look Y-shaped, similar. Only thing is that the lines are shifted slightly relative to each other. But if you watch carefully, things become slightly clear that there are differences. One difference is that the curve corresponding to the equilibrium between solid carbon dioxide and liquid carbon dioxide shows a positive slope, whereas the same line in the case of water system has a negative slope. Let us look for the reasons why the slopes of the lines are different. Now, we know that density of ice is less than that of water. That means specific volume of water is less than that of ice. That is why ice floats on water. Hence, when ice is subjected to pressure, there is a natural tendency for ice to relieve the applied stress. This comes from Le Chatelier principle. So, ice starts melting. This way, it can reduce the volume. So, melting is an endothermic process, we know. The heat for the melting comes from the system itself. If the heat is taken out, the temperature naturally drops, and hence the slope of the line tilts towards left. That means a negative slope, and because of that, liquid water can now exist at lower temperatures, and it continues as the pressure is increased. The melting point of ice continues to decrease. Whereas, in the case of carbon dioxide and most of the other substances, the reverse is true. Solid phase is denser than the liquid phase, and hence increase in pressure favors the solid phase, and that gives a positive slope to the curve. If you look for another difference, it is the triple point of carbon dioxide system lies above 1 atmosphere. It is 5.11 atmosphere. You can clearly see by comparison, it is much above that of water. What does that mean? What is the implication? Implication is that we will not be able to see liquid water at 1 atmosphere. Even if you have a cylinder of liquid carbon dioxide filled, and if you try to empty out, from the nozzle, liquid carbon dioxide will not come out. You will be able to see only flakes of solid carbon dioxide or the gas that escapes, because at 1 atmospheric pressure, carbon dioxide can be only in solid or gaseous state, can never be in the liquid state. Solid carbon dioxide, if you keep on an open table, That means you are exposing solid carbon dioxide to atmospheric pressure. It sublimes, it disappears without leaving any trace, whereas our normal ice melts to give a pool of water. Both look alike. We will not be able to distinguish which is solid carbon dioxide and which is ice, but then once the ice has melted, the solid carbon dioxide must have just disappeared, and that is the reason we call solid carbon dioxide dry ice. It can be put to use. One application is for transporting ice cream to long distances. You can use a refrigerated van, but it is expensive. But pack ice cream with the dry ice at 1 atmospheric pressure. The temperature corresponding to dry ice and vapor or gas is minus 78.5 degrees centigrade. The ice cream is kept safe without melting, but eventually the dry ice simply disappears. That means you have produced very low temperature, but the things remain dry because solid carbon dioxide has just disappeared from the scene. Thus, the dry ice has twin advantages. Look at here, the dry ice which sublimes, whereas our ice melts to give a pool of water. Before I move on to the next system, I want to tell you about supercritical carbon dioxide. The region beyond C, the critical point. This is a very good solvent for lipophilic compounds and hence used in extraction, and also you might have heard about a chromatographic method called supercritical fluid chromatography. Supercritical carbon dioxide finds extensive application there as well. One, it is less toxic, another, it simply sublimes. Let us move on to another interesting phase diagram, the sulphur system. We are adding some complexity as we go to sulphur system. It is also a one component system like water system and carbon dioxide system, but it has two solid forms. We have seen in the case of water also several solid forms of ice, but they come into existence only at very high pressures. But in the case of sulphur, there are two solid forms, rhombic sulphur denoted by SR and monoclinic sulphur SM. These are the two polymorphs or allotropes, which are nothing but two different crystalline forms. Polymorphism is the phenomenon which is now has become a big issue in pharmaceutical industry, because many of the drug molecules show polymorphism. Not in this particular case, we are interested in rhombic and monoclinic sulphur. If you heat rhombic sulphur, you can convert that into monoclinic, and if you cool it, you can get back your rhombic sulphur. That means it is a reversible change, and this transition occurs at 96.4 degrees centigrade. Such a phenomenon is known as anisotropy. That means in this sulphur system we have four phases, two solids, one liquid and one vapor. Let us apply phase rule directly. There is one phase equilibrium corresponding to rhombic sulphur, monoclinic sulphur, liquid sulphur and sulphur vapor. Phase rule tells us that the system is bivariant, and it is represented in the diagram with the four areas in which the four forms come into stability. 1, 2, this is monoclinic, vapor and sulphur liquid. Needs no explanation now that you are familiar with carbon dioxide and water system. Two phase equilibria, if you look at, the system is univariant. You have 1, 2, 3, 4, 5, 6 lines. You can identify that in the phase diagram. AB is the sublimation curve of rhombic sulfur, BC is the sublimation curve of monoclinic sulfur, and curve BE is the transition curve where rhombic and monoclinic can be made to convert into each other. You have CD, it is the boiling point curve of liquid sulfur, and this CE is the fusion curve or the melting point curve of monoclinic sulfur, and EF is the fusion curve of rhombic sulfur. In all, there are 6 lines that are predicted, and we can identify them easily in the phase diagram. Now, 3 phase equilibrium. When there are 3 phases, number of degrees of freedom becomes 0. The system is invariant. We can recognize rhombic monoclinic vapor, rhombic monoclinic liquid, monoclinic liquid vapor, and rhombic liquid vapor. We expect 4 invariant points. These are the 4 triple points in the sulfur system. 1 rhombic monoclinic vapor, 2 monoclinic liquid vapor, and 3 rhombic monoclinic liquid. But where is the 4th triple point? Nowhere to be seen in the diagram. Phase rule has never been violated. If it says there are 4 triple points, they have to be. It is for us to find out where they are. So the question remains, where is the 4th triple point? And the missing triple point is this: rhombic, liquid and vapor, they cannot meet each other because monoclinic comes in between. Phase rule says if you cannot find the triple point in the stable equilibrium conditions, look for metastable equilibrium. That we have seen in the case of water. Liquid water at -5 degrees centigrade, so called supercool water, it is in the metastable state. Similarly, if we carry out an experiment in which rhombic sulfur is heated rapidly without giving sufficient time to get it converted into monoclinic sulfur, it directly melts. Conversion of one solid into another solid requires restructuring or reordering of molecules. If you do not give time for such a reordering, total disorder takes place. Therefore, rhombic directly gets converted into liquid, and we can establish this rhombic liquid equilibrium. Similarly, other 2 equilibria, metastable equilibria, can be made and traced so as to get an intersection of 3 metastable equilibrium curves at point G. 1, this is the metastable curve at which rhombic gets directly converted into liquid, and you have a metastable part here which is the extension of sublimation curve of rhombic sulfur, and you have the extension of vapor pressure curve of liquid sulfur. The 3 will intersect at the point G, which gives us a triple point, but this triple point is different from other 3 triple points. These 3 are BCE are stable thermodynamically, whereas G is a metastable triple point. If monoclinic sulfur were not there, because we said that we are directly converting rhombic into liquid, that means there is no intervening monoclinic sulfur. How the phase diagram will look like? This looks like exactly the phase diagram of carbon dioxide. That is the reason why carbon dioxide phase diagram is taken as a representative of one component system phase diagrams. Again, as I told you, let me remind, water is an exception where it differs from carbon dioxide phase diagram. Here are the values for the 3 triple points, the pressure and temperature, for those who are interested in remembering the values at which these 3 triple points exist. Let us try to illustrate how the changes take place when you go from rhombic sulfur. We are here with the 2 degrees of freedom with us. We are fixing pressure to be 1 atmosphere, we are still left with 1 degree of freedom. We can use it to increase the temperature. As we move along this line, system will not resist because it is a bivariant system. Arbitrarily we can fix both pressure and temperature. As we move along this line, we reach a point on the line BE at which monoclinic sulfur makes its appearance. Now there are 2 phases, it is a 2-phase equilibrium. We lose 1 degree of freedom, we are left with only 1 degree of freedom which we have already used in fixing the pressure. The temperature cannot be other than the value given here, because the system says that there is no degree of freedom, the temperature cannot change. Whatever heat that is supplied is utilized in converting rhombic sulfur into monoclinic sulfur. When this conversion is complete, when no more rhombic is left behind, we have only 1 phase, that is monoclinic sulfur, we regain 1 degree of freedom and the temperature can again start rising. You can move along and then this can continue till you reach another point on the curve CE, at which the liquid sulfur makes its appearance. That means monoclinic sulfur starts melting. It becomes a 2-phase system. You lose 1 degree of freedom and it becomes a univariant system. You have utilized that in fixing the pressure. Temperature gets arrested at this point. That is why monoclinic sulfur has a sharp melting point. And then when the melting process is complete, when no more monoclinic is left, the temperature can start rising again, and this will continue till you reach another point on the curve CD, which is the boiling point curve or the vapor pressure curve of liquid sulfur. There is a temperature halt, temperature arrest, because now there are 2 phases in equilibrium, liquid sulfur and sulfur vapor. The temperature becomes constant when the vaporization is complete. When no more liquid sulfur is left behind, we regain 1 degree of freedom and temperature can rise. This is how we can utilize the phase diagram to explain the changes that are taking place. Similar explanation can be given as we move at constant temperature. If we change the pressure, what happens? The descriptions are very similar. Now let us try to use our knowledge of phase diagram of sulfur. See, in geology, if you look at the deposits of sulfur in nature, you find very large crystals of rhombic sulfur. If the transformation is through monoclinic sulfur, as I have shown here, if you follow this path, we end up from liquid to monoclinic to rhombic. Now, when the earth was formed, it was at a very high temperature. Most of the substances were either vapor or in the liquid state, and as things started cooling down, if the conditions were as per this line, we would have gone from sulfur vapor cooling to sulfur liquid, condensing to sulfur liquid, and then crystallization of monoclinic, and then transition from monoclinic to rhombic sulfur would have taken place. This would have resulted in smaller crystals of rhombic sulfur, but there are larger crystals in the deposits. Therefore, we can find out the conditions under which such a change must have taken place. Definitely the path followed in this case must be corresponding to conditions much above this triple point E. So, at which liquid sulfur slowly, as it is cooled, gets transformed into rhombic sulfur, giving sufficient time for the rhombic sulfur crystals to grow to very large extents. We are trying this in the lab also. If you want to grow a crystal of, say, copper sulfate or sodium chloride, we have to slowly grow it, taking a saturated solution, and then without disturbing, it will grow into larger crystals. Similar thing must have happened in nature, where you had sufficient time and conditions favorable for the growth of larger crystals of rhombic sulfur. Now, one thing that we have not tried to answer, or never bothered also. We said that sulphur system has 4 phases, 2 solids, 1 liquid and 1 gas. Is it possible for the 4 phases of sulphur to coexist in equilibrium? What is that equilibrium? Sulphur rhombic in equilibrium with sulphur monoclinic, in equilibrium with sulphur liquid, in equilibrium with sulphur vapor. How will you answer this question? Go back to phase rule equation. It is a 1 component system, C is 1, and if P is 4, the phase rule equation tells us that F is equal to 1 minus 4 plus 2 is equal to minus 1. But we know that number of degrees of freedom cannot be negative. Therefore, 4 phases of sulphur can never coexist in equilibrium. We have only a 3 phase equilibrium, any 3 combination. In general, we can make a statement that for any 1 component system, the maximum number of phases that can coexist in equilibrium is 3. Let me give a practice question to you. Now that you are familiar with 3 phase diagrams, water, carbon dioxide and sulphur, it is appropriate for you to test your own knowledge. Like sulphur, gallium metal also shows 2 different solid phases. The schematic phase diagram of gallium appears as shown below. It is a very schematic diagram, but you can recognize all the features that you have seen in the 3 diagrams that you have studied. Identify the regions, how many triple points are there, and at 1 atmospheric pressure, which phase is more dense, solid or liquid, and give an explanation for that. Before I sum up, let me tell you about 2 important phase diagrams, carbon and helium. Extremes. If you want to study carbon phase diagram, you have to work at very high pressures and high temperatures. If you have to work on helium system, you have to work at very low temperatures and very low pressures as well. If you are interested, you can refer to books to know more about it. Let me summarize what we have studied today. We extended our discussion on 1 component system. First we studied carbon dioxide system and then the sulphur system. In my next lecture, we will go a step forward and start with the 2 component systems. Very interesting. Till then,